recently, one of my friends made the unfortunate mistake of asking me to teach him how to program in C, and it just got me thinking about like how I would go about that, right? And so I'm making this video just as kind of a jumping off point. If you already know how to program and you want to start doing some of the stuff that I do in C, like here's what you need to know, right? And I would really just say, like, in terms of why you would want to learn C, I always say that if you're good at C, you're good at how computers actually work. Like if you know how to program well in C, you know what computers are actually doing. And I feel like, I don't know if C is necessarily like the best language or like my favorite language, but it's just the language where I feel like there is the least friction between like my ideas and the actual commands executed on the CPU, if that makes sense. But let me just get into the basics here. So like literal basics, if you want to printf hello world, right, in C, what do you have to do? First thing you're going to do is type hash include. This is what's called a preprocessor directive. I'll get to that later. But basically this is telling the compiler like we want to be able to use these functions. And then what we're going to include is std for standard and then IO. So standard input output.h. And this will give us the functions that allow us to print to the console. And then for our main function, it's actually going to return an integer, which is kind of weird. My friend, when I first said this, kind of confused him. But it is basically just like the exit code of a program. So like when you run a program, it returns a number to indicate if it was successful or not. So you don't have to include a return 0. It returns 0 by default if you don't. But I just do that anyway. So like if you had some error, you could just return 1 if it's like a simple command line program, right? So then to actually print the function is called printf. That's print, and then f is for format, but you can also just pass it a string. So specify a string in quotes, and then you'll say hello world, and then you have to explicitly pass in a new line. It doesn't do the new line automatically. So this is what the hello world program looks like. And then open up a terminal. So I mean, depending on like what operating system and what IDE or whatever you're using, you might not actually need to use the terminal to build a program, but I think it's still very powerful to understand how the compiler actually works, and you do that with the terminal. So there's a few compilers. The main ones that you'll see are Clang, which stands for C Language Compiler. That's from LLVM, and then GCC, GNU C Compiler. Clang and GCC like generally are pretty interchangeable. I know people might get mad at me for that, but compared to the MSVC Microsoft's compiler, Clang and GCC are very similar. I personally use Clang. Clang works well on Windows, and Clang feels a little more modern, but Clang and GCC are both pretty good. So type in the name of your compiler, and these command line arguments I'm giving you are only going to work for Clang and GCC. And then you're going to do the name of your source file. So right now it's main.c, and then -o. Or actually, you can just type this. So if I just type this, this will generate this file a.exe here. On Linux or Unix, it'll generate a file called a.out. So a is just the default name. So if I run a here, you'll see it'll print hello world, right? But most of the time, you want to actually specify the name of your program. So you do -o, lowercase o, and then the name of the program that you want. So I'll call mine main.exe. If you're on Unix again, there's no extension, I think, for files. I mean, I guess you could do like elf or something, but main.exe is required when you're on Windows. And don't say the output is main.c. My friend did that. Just say main if you're on Unix, or main.exe, or whatever you want the name of the output program to be, right? So now if I run main.exe here, it'll print hello world, right? So that's just the basics. Now getting into what are the actual basic types that you want to use in C. And this is like one of the first points where the 50 or so years of tech debt actually catch up to you. There are built-in types. Like this integer right here is a built-in type to C, but if I'm not mistaken, like there are no guarantees about how big it is or anything, so just ignore all the built-in types. What you're going to do, come up to the top of your file and include standard int.h. And what this file will give you is a bunch of integer types with guaranteed sizes. So you can type int32.t, int16.t, and these are like, it specifies the number of bits. And then you can also do uint to get an unsigned integer. So it just makes it like leagues easier and also probably more portable. Like I said, there's no guaranteed size for int, but it's probably going to be 32-bit signed on most platforms nowadays. And then the other thing that I do, you'll see at the top of all my code for all my videos, is I like to type def, which just is like a way to rename a type, or not rename it, but give it a new name, to a more compact version. These are, as so many generous people in the comments have pointed out, I do use the same naming convention as Rust, but this is just so that I can type out my integers faster. So I'll go ahead and do this at the start of every project for 8 all the way up to 64, like so, and then same thing, but for the unsigned ints, where I'll have these be U instead. So yeah, so type def basically says this name on the right, the keyword on the right now is equal to the keyword on the left when it comes to types, right? And then just for consistency's sake, I do like to type def float and double to follow the same naming convention. This is something that's not necessarily guaranteed, although like IEEE floats are 32 point. So you might want to like do a static assert to make sure there's a right. So these are the basic types that you're going to be using. Like the U32 is going to be like your workhorse type. If you have a number of things that's less than 4 billion, it should probably be a U32. Like U64, you'll commonly use that when you're dealing with like memory and like a size of memory, all that stuff. But these are the types that you should be using, right? And if you're not familiar, so these top 4, these are signed. That means they go from negative to positive. These are unsigned, so they go from 0 to positive. So the unsigned integers have double the range, or like double the magnitude, positive, but they have no negative numbers. So like an I32 goes from negative 2 billion to 2 billion. A U32 goes from 0 to 4 billion, something like that, right? And one more thing in terms of basic types. If I type in true, you'll see undeclared identifier true. True and false are not defined by default. I love C. So to get that, you want to include stud bool.h. And that will define true and false. That will also give you a bool type. Although for consistency's sake, I like to use my own bool types that are size. So I'll have a type def for a B32 and a B8. And if you have like a function that's returning a Boolean, you could do a B32 or a B8. It really is not, I don't think it actually affects the code gen that much, especially on modern platforms. So like you may, I know beginners oftentimes think like you're saving space by using less bytes, but in practice, if you're like returning a Boolean from a function, it doesn't really matter, right? But these are the basic types. This is what you should be using all the time when you have some number in C, right? Now, the next thing in C that's very important, and this one is pretty different from like most other languages that you might be used to if you already know how to program, and that is what's called a structure. So to define a structure here, well, first I'll start with this. You can use the struct keyword to define a structure, and then I'm going to do like a quick vector type. So I'll have a 2-dimensional vector, and then in the structure definition, you define each of its members. So each member is just a type and then a name. And basically, if you're not familiar with structures and you've gone through like the classic learning to program, I can just say that structures are basically like classes but without functions, but you should never think of it like that. Structures are just grouping of data, right? And this is where we get to, in my opinion, the biggest shift between programming in a systems programming languages like C versus any other programming language, and that's you should be thinking about data, right? C, when you program in C, you realize that a program is just something that transforms data, and a struct is just plain data. So there's no ancillary stuff here. If I have a vec2 and I make some variable that is of type vec2, it's going to be 8 bytes, and it's going to have 4 bytes of that be the x and 4 bytes of that be the y. There's nothing else, right? Although here again we get to some of the weird stuff with C. If I just type vec2v here, you'll see that it doesn't like that, and you actually have to type the keyword struct on each instance of it. So instead of that, what you can do is use the syntax type def struct and then put the name of it at the end, right? Now, sometimes in certain situations, especially in like a linked list or a tree type thing, you want to be able to have a pointer. Actually, wait, I'll cover that when I get to pointers, not right now. So now that we've done this type def, we can just use the vec2 keyword here, and that will let us create it. And then to actually initialize a structure, there's a few different ways you can do that. So the first thing is, well, all of them are with curly braces. And the first way you can do it is just to type in the first like argument, or like the first field and then the second field, just one after another, right? So now like this will have our vector v will have x is equal to 1 and y is equal to 2. And you know, for this, it might actually be worth it to set up a print statement. So if you're not familiar with C, the printing is really stupid. Basically, in this string here, we'll say that our vector is equal to, actually, here, we can use angle brackets, I guess that's the convention. Instead of having like some syntax or anything to like actually do nice formatting, basically in this string, if you prefix something with percent, like %f stands for percent like floating point, then it'll indicate that there it'll insert a floating point number. And then to actually give it the what should go in the format, those are the next arguments of the printf function. So the first percent sign here for %f corresponds to the first argument here, v, so it's a floating point number. Then the second %f corresponds to the y, the v.y. So yeah, I mean, just look up like online how printf works for like different types that you might need. But %f for floats, %d for integers, %u for unsigned integers. Yeah, so now I'm going to go over here and we can say clang main.c. I'm just going to keep it as a because that's easy. So now we can see that our vector has 1, 2, right? But this is not very flexible, right? A lot of the times we want to be able to specify only some of the members, or like specify it in a different order, or maybe we just forgot the order. So C has a very nice syntax for selectively initializing members. So you can say dot and then the name of a member. So I'll say dot x equals 1, dot y equals 2. Actually, we can do like 2, 1 so that we get a different output. So now when we do this, you'll see, I mean, just saying the vector is 2, 1, right? But the cool thing about this is that it is like agnostic of the order. So this, I just swapped those two lines, but the vector is going to be the same because I'm specifying what x and what y are explicitly. And then the really cool thing about this, and this syntax is called designated, or it's a designated initializer, I believe, is that let's say I don't actually initialize x here. I just leave that entirely blank. What will happen? If we run this, you'll see that x is actually 0, right? So this is really cool, and this is really, really powerful once you start doing more complex stuff, and you'll appreciate this more and more as you program. But anything that you don't specify here automatically gets set to 0, which is really, really cool. And by that I mean like the literal bytes are 0. It just so happens that in the IEEE floating point format, all zeros does equal 0, which is also very nice. Now, one issue with this syntax is that if I try to do this again, and if I say like dot x equals 3, dot y equals 4, or whatever, now we're getting an error, right? And the error is because it doesn't know what type this is. So what we can do is use the typecasting syntax, which is the same as Java, and just include what the type of this thing is. I don't know if it's actually typecasting in the sense that you would typically think of it like that, but it's just what you have to do when you're not like initializing it right after declaring it, right? So now here you can see we'll run this, and we're resetting vector, right? And obviously you don't actually have to like reinitialize everything the whole time. You can just access the members directly. You can say v.y equals 0, whatever, right? So yeah, its structures are just grouping of data, right? Very, very easy. So now that we've got structures, what I want to go over, and this might be the like biggest jump if you have not done a systems programming language before, and this is also one of the most important concepts in C, and that is pointers. Okay, so what a pointer is? Well, here let me start with this. Let's say we have some integer x equal to 1, 2, 3. This integer x lives in memory somewhere, right? It is, when we run the program, there is going to be 4 bytes in your physical RAM that is equal to 1, 2, 3, right? And what a pointer is literally just a number. A pointer is just a number, and the number corresponds to the address of a variable. So let me show you what that means. If I take I32 and then I'm going to do an asterisk, the asterisk denotes that this type is a pointer, and I'll call this px. And as a side note, the asterisk can be on next to the I32, next to the p, next to the variable name, or just in between. Everybody has different conventions. I put it next to my type name like that. And then to get the address of a variable, you use the ampersand. So now what we have these two variables. So I32x is a 32-bit signed integer whose value is 123. And then px is a pointer, which again is just a number. A pointer is all a number. That's all it is. And that number corresponds to the address of x. So let me print this out. Like I said, %d prints out a number, an integer. %p prints out a pointer. So I'm going to print out x and px like this. And you'll see that our variable 123 here is at this address in memory, whatever that means, right? And this is going to be different each time we run the program. I don't know why I did that. Different each time it runs the program, right? But the key idea is just it's a number, and this number points to the address, okay? So how do we use this? There's a few different ways you can do. So first thing that we can do is actually modify the value at the address. So that's called dereferencing. If we have the pointer here and we want to set its value, or if we want to set the value at its address, what we can do is prefix this with an asterisk. This is where the syntax gets very confusing because the asterisk is used both to define the type and to dereference it. But the asterisk basically says, go to wherever this is in memory and then set it to this value, right? And this is why you do need a type on a pointer. Well, I mean, actually, you don't need a type on a pointer. Technically, you could have a void pointer, but don't worry about that right now. You should have a type on a pointer so that when you're dereferencing the pointer, it knows how that memory is laid out, right? Because if this was a float pointer, it would be different, right? So now what you'll see when we run this, so the first time we're printing this, it's just going to be whatever the value of x was, 1, 2, 3, and then the pointer. The second time, we haven't touched like x, the variable, in our code at all, but we've still modified that address in memory. We've modified like the memory there, right? Through the pointer. So the pointer will be the same, but the value of x will be different. So you see here, the first time we have 1, 2, 3 at x, the second time we have 3, 2, 1 at x, and then both times the pointer itself is the same. So this is like what a pointer does. You point to that spot in memory, and then you're able to modify that spot in memory however you want, right? So another thing that you might want to do is have a pointer to a structure. So if we go back to our vec2 here, and I have some v that's 1, 2, then what I can do is make a pointer to our vector like this. This is a very common thing to do, especially when you have a function, because if your struct is a lot larger than 8 bytes, as ours is here, you don't want to have to copy that whole structure into the argument of a function. You just want to have a pointer to it. So this is a very common thing, dealing with a pointer to a structure. And obviously, you can access the members by first dereferencing the pointer and then accessing the members like so. So if we set this like our x to 3 and our y to 2 or whatever, here we print f our initial vector, and then we can do our vector after doing this change. Boom. So we've modified our vector, but obviously this syntax is very, very clunky. So C actually has some pretty cool syntax to simultaneously dereference a structure and access its members. So here, let me actually go back. So this thing here, the dereference and memory access, is equivalent to saying PV and then using this arrow syntax, right? Just a dash and like an angle bracket. That dereferences it and accesses the member. So this code is literally the same. It's just a lot easier on the eyes, right? So that's if you ever have looked at C code and seen a bunch of arrows, that's why, because we were probably dereferencing some pointers. All right, so now here is where pointers get really weird and also kind of confusing, and also like memory unsafe, yada yada. But before that, let me show you how you can do an array. So if I have, I'll say nums here. The declaring an array, I think this is kind of similar to Java. You're going to say int nums, and then in this angle bracket you can specify a size or you can leave it blank, and then here you'll have all of the values here, right? But here's the thing. nums the variable is not a structure. It doesn't have anything else, or like it's not like in most languages. If you have this thing, you could do like nums.length or like nums.size or whatever, or like any of that. But in C, there's nothing like that built in. So what nums is actually just a pointer, right? Actually, I don't know why I did it in there. It should be I32. Nums is just a pointer. If I here I can print out we can print out each number here, and the axis in an array is the same. Something like that. Oh, yeah. Array access is the same as like any other language. You use the square brackets, but we'll get into what that actually means in a second. So, yeah, you can access the array here. If I say dereference nums and set that equal to, 6 or whatever, and then print out our array again. Now you'll see it's modified that first element. So nums the variable is just a pointer to this one here. It's just a pointer to the first element, which is really weird. So that begs the question, what does what does the square bracket thing actually even mean, right? And the answer is that it both dereferences value and does some math with the pointer. So because pointers are just numbers, you can do math with them, which is weird. But if I take nums and I add 1 to it, now we're getting, now this right here, nums plus 1, is another pointer, and this pointer points to 2. So if I set this to 8, right, and then compile this again, you'll see that we get 1, 2, 3, 4, 5, the initial one, and then we have 6, 8, 3, 4, 5, right? So adding any number to a pointer offsets it by that many. And this is another area where the type of a pointer is very important, because if you'll notice, an I32 is 4 bytes long. So the pointer arithmetic works on increments of the pointer size, not on bytes. That's very important. You have to watch out for. So this +1 actually increments the pointer 4 bytes in memory. So that means that here, if we wanted to do, let's make a quick for loop for all the elements of the list. What we can do, we can use that thing we just did, num plus I, dereference it, and then here, why don't we do 5 minus I. So now we get 5 to 1. So yeah, this is just the same as dereferencing it. So that means that nums I is equivalent to nums plus I dereferenced, right? That's literally what array access is. And I think, wait, let me see. I'm pretty sure because of that, you can also swap these, which, oh shoot. Because this literally just says take this, add it to this, and dereference, right? This is, I index nums is technically the same as nums index I. But obviously don't write code like that. I'm just trying to prove a point here. So this is how arrays work. There's no information about length. There's no information about anything except for what the type is and what the first element is. So that means you could, for instance, say nums equals whatever, right? Now, the compiler's a little smart here because nums is statically defined, and it knows that I shouldn't be doing that. But, this program's not going to run. It doesn't do anything. It doesn't work. It just crashes. And that's because there's no, it just doesn't care. The C lets you do literally anything. So you can just, and because accessing an array is just pointer arithmetic and dereferencing, there's nothing wrong with doing that, according to the language, right? Because of this, if you ever have an actual array in a C program, you should always, always, always include a length alongside it. So if I had some structure here of num array, right? it'll have some pointer nums and then a size, right? Like these should always come in pairs. There should never be a situation where you just have the raw pointer and no size information. And this is actually what gets into, if you've seen my video on length-based strings, this is why I don't like C strings. But that's a little more complicated past the basics. So this is why people say that C is like dangerous and stuff. But there are actually there's a few tools we can use to make these issues like way worse, or way better than people would imagine. And the first one is called an address sanitizer. And that's just a compiler flag called it's -f sanitize equals address. Sorry that it's so dark on my, I don't know why PowerShell does that. But if we compile that with our address sanitizer on, it'll insert a bunch of stuff in that like checks whenever you access memory. So this is obviously something that you cannot have in production. But now you can see that instead of the program just quietly failing, we actually get an access violation here, right? Although you'll still see we're not getting any useful information here. It's just a bunch of like memory addresses of the assembly. So what you can do, in addition to including the address sanitizer on, what you're going to do is compile with debug flags. So to do that, you do -G. I don't know why it's G, but -G gives you debug information, and that allows any program like a debugger or even the address sanitizer to like see what lines of code correspond to what assembly instructions, basically. And another thing that you're probably going to want to do if you're compiling in debug mode is to say -O, big O this time, capital O, which stands for optimization, and then 0. So -O0 says don't optimize anything, right? So -G, -O0 is like your typical debug build flags, and then the F sanitize equals address turns on the address sanitizer. So now what you'll see is that, hopefully my head is not covering this up, but we're getting some, we should be getting some good error messages here. Yeah, so we see it happens in main.c, line 29. Wait, did it actually? Did it show the line number before? That'd be kind of funny. Yeah, okay, no, we're not, it does not give you, you do need to do the debug symbols, that's what I thought. But this is also a good time to mention, if you're doing C, you should have a debugger. You should know how to use your debugger well. On Windows, I really recommend rad debugger. Here, let me increase the view here a little bit. Rad debugger, I think right now only works on Windows, but basically you just like go to whatever directory, find your executable, and then we can launch and step into it. So it looks like the rad debugger is not actually playing nice with the address sanitizer here, so I went ahead and just compiled it with the -G and the -O0 flags. Although, I don't know, in my actual projects I haven't noticed as much of an issue with that. But now you'll see like we're stepping in and you get the same information, right? You can even just run the program and it'll also break on that line. So honestly, I feel like I've heard some people that just always running their programs to need debugger. That might be the smart thing to do, but it just lets you like catch anything. And yeah, definitely know your debugger. On Windows, you have rad debugger. I think that's the best option. On Linux or Mac, you can use like GDB or LLDB. Those are console based. Or you could just wait for rad debugger to come to Linux, because I think they're working on that. But yeah, arrays include, make sure to include a link with arrays, so you're not accessing out of bounds. Next up is how you can actually allocate memory. So thus far, I've only shown you like allocating memory that you know at compile time. But a lot of the times you might have something from the user that you need, and it's like how do you allocate a dynamic amount of memory? Or if you have like a really large amount of memory you need, probably shouldn't do that just yourself or like just on the stack. So this might surprise some people, but I think what you should do if you're just starting out is actually use malloc and free, and I'll show you how that works. So it's stdlib, I think. So let's say that you want to allocate like 1,000 of these vector structures, right? So first thing we'll do, I'll have a num vectors, or yeah, and I'll say that's 1,000. and then we'll have our actual pointer to the vectors. And this, to call this, we'll call malloc. And then all malloc does is it takes in a size in bytes to allocate. And it returns a void pointer, which is just a pointer that doesn't have a type. So I mean, generally it's best practice to cast that, although it's not that important. So we want to get from a number of vectors to a number of bytes. So to use that, we use the size of keyword. This is not actually a function. This is something that happens at compile time. But you just pass in the name of a type or even the name of a variable. So the size of that and then times the number of vectors that we're using. So now here, our vectors, this memory is now valid. We can write to all of them, right? And again, this is like where the sizing information comes important. If you're always doing operations on arrays in a for loop, like you have already done the bounds checking, because that's just naturally how a for loop works. So we'll say that our vectors I, we can say dot x equals 1, or like here, I times 1, we can do like I times 2 or whatever, and you're free to use this memory however you want. And then when you're done with it, this is the key, and this is where it might differ from like the new keyword in Java or C# or something, is that you have to manually tell C that you're done with this memory. You have to free it, right? So as you can imagine, this can make managing complex lifetimes and stuff really complicated in C. But I still think when you're first learning, if C is your first manual memory management language, you should do something non-trivial with malloc and free. You should get a feel for how this actually looks like and why people advise against it. And then once you're done with that, go watch my video about arenas, or look up Brian Fleury's article about arenas and use arenas instead. But I think you should at least once get a feel for like what it actually feels like to use malloc and free on a regular basis. Because I don't know, it's interesting, and you also see why it caused so many issues. You see why C++ is the way that it is. You see why Rust is the way that it is. You see why garbage collection got so popular. All of that stuff just because malloc and free is symmetric. Yeah, and this is another reason why, because when my friend, when I was first telling him about pointers, he was like, why do you even need this if you have like the initial, like the variable itself anyways? And it's because of stuff like this. When you're dynamically allocating memory, there's no actual variable there that we can access without the pointer, right? So you only have the pointer. So now for some stuff that's like more kind of C nonsense. And this is some stuff that you just have to know because it's weird. But let's say I make some function, call it foo, and I declare it down here, and this just prints hello, or whatever, right? That function exists, but if I come up here to main and try to call foo, you'll see I'm getting an error here. It says undeclared, call to undeclared function foo. What does that mean? The function's right here. How is it not declared, right? And the thing is, C literally processes your file top to bottom. So if foo doesn't exist above where I'm calling foo, foo literally doesn't exist according to the language. So I have to move this function up here so that I can call it, right? That seems weird, right? That is weird. No other language is like this to my knowledge, but you have to do it like this. But what if foo has like a bunch of stuff? What if we really don't want it above main? Well, what you can do is what's called forward declaration. You can just say the name of the function, the return type, and the arguments, and then just put a semicolon there. Don't even put the body of the function. And this just says, hey, C, this function exists, right? So don't get mad if someone calls this function. This function exists. And then you actually declare it later, right? And this really gets into, like, this is a whole rabbit hole of how C works and how, like, compilation units and linking, yada, yada, yada. But what you have to know is that the function has to come above where you're using it, right? And that's where you get to these .h files, right? Like, in literally every other language, like in Python, it's a py file. In Java, it's a Java file. In C or C++, you have two different file types. Like, why is that? Well, it's because if you're splitting code across multiple files, you have the one file called the header file where you actually declare a function, And then you have another file, the source file, where you actually put the body of that function. Right? And this gets into a little bit of like how build systems work, and this is a whole rabbit hole that I'm not going to cover right now. And then here we should also include foo.h. But like the traditional way of doing this would be that you can compile main and foo.c separately. But you can also do, in the compiler, you can include multiple source files. So here we should also make sure that we're actually calling foo. So I'll call foo here. And then when you are doing it with your own file, you have to use quotes for the include, not square or angle brackets. Just a note there. So now what we can do is I'll say clang main.c, foo.c, and then, yeah. So now we see that we're printing hello world, and we're doing that from the separate file. So there's a lot to get into that I'm not going to get into right now, but just like look up like what a compilation unit is, how build systems work, header guarding, all of that stuff. And then after you get confused by all of that, go watch my video about single compilation units and realize that you can make it 10 times simpler. But I'm not getting into that right now. We're almost done. There's just a few more things that I want to mention. First of which is what's called the preprocessor. And I mentioned this a little bit at the very, very start when I talked about include. The preprocessor is basically like a text engine that runs before your file is compiled. And if you ever see a hashtag at the start of the line, that indicates that it is something to do with the preprocessor. And so the two most common things that you do with the preprocessor are include directives and macro definitions. So if I say hash define, well, there's a few different ways to do this. First, I can just say foo, and then like at the name of something. The naming convention for macros is to have them all capitalized, and then a space, and then whatever the value is. So now if I come down here and I say x equals foo, the preprocessor, it'll scan the file before the compiler gets to it, see define foo123, and then textually go ahead and replace every single instance of the text foo with whatever text followed this, right, up until the new line. So here you can see on my language server it's saying that foo is just 123, so that x is just 123, right? And you can see that here. Like so, it's just 123, right? The other thing you can do is you can actually have a macro that takes arguments, right? So if I have a min macro that has a and b, I can say a less than b, a, b, right? And if you are already familiar with C, you'll know that's incorrect, but we'll get to that in a second. But now what we can do is if I have some I32A equals 1, I32B equals 100, whatever, and I can print f the min of a and b. Like so, you get the min, right? And if you, again, if I use my language over here, you'll see below there it says expands to, actually wait, maybe I shouldn't have called these a and b as well. Let's say there's x and y. You'll see it expands to x less than y, question mark x colon y, right? But the key thing, the thing that you will shoot yourself in the foot for, is the fact that the preprocessor is only text. This looks like a function. It, like in every way, it feels like a function, but it is not a function. If I instead say like 2 times x here, right? Now, actually, well, maybe that's not the best example because that would actually work. But if I, instead of a variable here, if I have some sort of expression, that expression will get like pasted in a way that this might break. So what you'll see in macros is that every single variable that you want to act as a variable gets wrapped in parentheses. So that way it's actually executed in the correct order. But this even still might not be correct, because if instead of x and y I have like x, that's instead lib. If I have some random number, now you'll see in this macro when it expands to, it's now calling rand twice. So it doesn't work as a function. It's not like the arguments are evaluated and then passed in. No, it's just text. So macros are really powerful and they're really stupid if you don't know what you're doing. And a lot of the times you think you know what you're doing and you don't. But for select cases like min, if you know that it's textual and you're not going to pass rand into it, you can use macros. And they can be helpful for stuff. So like in my files, I'll like min and max. Another thing you can even do here, I'll show in a real project that I have, I'll have a header file that like defines all of this base stuff. So you can see I have all my type defs here, and then I'm defining a bunch of macros here, right? You can see my min and max just like I did there. But the cool thing is, because it's textual, you can actually do some stuff that kind of feels like generics or templatey. Where this macro here, SLL, which stands for singly linked list push front, I'm taking like the name of some variables and then I'm just arbitrarily accessing a next member. But if I look for here, where's the base where I'm actually using it? So like here, this is a logging system. That's not actually, but you can see that. Wait, what is? Maybe that's not the best example. Yeah, this one. You see how in the macro, it's just kind of assuming that these variables have a next member. So that means that any variable that happens to have a next member, like these log messages here, it'll work for, right? So that's like the counter side to the text, like it being text replacement, is that it also allows for some kind of crazy stuff like that, where it kind of feels generic in a way that can be useful sometimes. But it also, of course, means you can shoot yourself in the foot a lot, right? So one final thing that I want to note, and this is a bit more of an advanced topic, is how you might do something akin to polymorphism in C. Because C, it doesn't have any inheritance, it doesn't have any notion of any of that crap. Which will actually end up making your program faster and will make you have to confront how a system like that actually works, right? It's not like you're going to have some random V table like messing up all of your cache coherency. So let's say we do, I don't know, what's a good example? Let's say we have some sort of structure that we want to have like a shape, right? I think I'm just like implicitly like thinking about the Casey Minotaur video about this, but we want to have like a rectangle, a circle, a triangle, I don't know, whatever, right? And what you can do is include what's called an enum of like the type of it. Well, I don't know, type is technically not a keyword in C, but I feel like it's still probably not the best. We'll say like kind, and then we'll say like shape, square, shape, circle, shape, triangle, whatever, right? And this, you can also define this enum like outside. One of the weird things in enums is that there's no guarantee as to like the size of an enum. So sometimes I'll have an enum and then I'll like have a type def on a U8 or something so that I can ensure the size of the actual instance of the enum. But either way. And then what you can do, so here we're going to have contents, or we'll have, So a union, it looks like a struct, but instead of all the members coming one after another, they're like all stacked on top of each other. So let's say for a square we have some S for side length, and then for our structs, for our circle we have some radius, and then for our struct triangle we'll have like a base and a height, like so. And the union basically says that all of these are just kind of stacked on top of each other. And that means that the size of the union is the maximum size of each of its members. So like the square here is just 4 bytes, but the triangle here is 8 bytes, so the union itself is 8 bytes, right? And the way that you could do this, you would have some shape, call it S, and then you'll just say .kind equals like shape circle, and then you'll say .contents circle .r equals 1, 2, 3 or whatever, right? And then if you have like a bunch of shapes, right? And you wanted to like iterate through the shapes, whatever, you would just have to do like a switch statement on the shapes kind, and then like do case shape square or whatever, right? I don't know, you can imagine how that would look, right? Okay, one of the nice things about using an enum is that it does actually, you'll get some warnings if you don't have all the cases covered versus doing a type def. But this is how you could get something akin to polymorphism in C. Now, the real thing that you'll notice is that oftentimes you can do better than actually having each of the types of this be its own structure and its own thing, and you can just like kind of share a bunch of the data. So that's more akin to like a fat struct kind of design pattern. But you'll notice that in each of these, we just have like one or two numbers that specify its dimensions, right? So what if I just say like dims or whatever, and now our same structure is still, it contains all this information. It's just you interpret the dimensions in different ways based on what the actual shape kind is, right? So that's where I'm saying like if you actually confront how you have to lay out the memory, you're probably gonna come up with a better way to do it, right? Or at least a more straightforward way to do it. But that's how you would kind of achieve something akin to polymorphism in C. Now, one final note I think I'll leave off this video with is, like I said multiple times, C lets you do literally whatever the hell you want. There are almost no limits on what's valid. Like I could literally create a pointer here that's just equal to 0, dereference this pointer and set it to whatever, right? Like it's so stupid. And you want to minimize the stuff that it's just letting you get away with. So when you're compiling a C program, you should always compile it with -w all to enable all the warnings, probably -w extra to enable extra warnings. This is slightly different between Clang and GCC as well. You can also do -pedantic, hopefully I spelled that right, to get even more warnings, right? So now it's saying like, oh, you should actually put void in there because it's not taking any arguments. But stuff like that, like where it'll just quietly let you get away with a lot of stuff. So do the W all, W extra, pedantic if you can to try to get a little bit more warning messages out of that. And again, if you see, here actually I can just pull this up in NeoVim. If I go to an actual makefile of a project, you'll see, first off, I've got the debug symbols on and the address sanitizer on, and then here I've got a bunch of warnings enabled. I have like some select warnings that I've disabled because they're like technically warnings, but every compiler supports them. So compile with as many warnings as you can, and you're going to get a much better experience. And then one final thing that I'll say is just if you're learning a new language at all in general, I think the best thing to do would be to just build a real application that's something that's non-trivial. And a lot of the times, if you want something more encouraging, it's like you should basically make a game, like a simple, non-trivial game like Minesweeper or something. So if you want to do that with C, I would recommend using Raylib. I think it's like a pretty easy to use, just kind of standard out of the box. You get some graphics, and that'll let you like actually get something on the screen, actually get something working, and play around with these concepts. Like figure out how to manage lifetimes with malloc, figure out how you want to structure some sort of polymorphic thing in your game if it necessitates that. Just like do something non-trivial, and I think Raylib is a great way to learn how to like get something on the screen and do stuff like that. Even if you like shouldn't necessarily use it in production. Although I don't know, maybe you should. I wouldn't, but I'm kind of crazy. All right, have a good day.